biomes, chapter 4, we're going to talk about climate and biomes. So make sure you know the difference between weather and climate. Weather is short term. Today, for example, I'm looking at my window and it's sunshiny in the 90s and there's a little bit of wind. That's weather. But climate is what happens over several decades at this time of the year. Not just looking at my window for today, but looking over time, 10 or 20 years, what happens in the location you're at, generally in the month you're talking about. So that's climate. So know the difference between weather and climate. So climate's an average, so it's going to be all the temperatures for this particular day of all the years over 10 or 20 years. And then we figure out, okay, well, in average, the temperature is this, and it can have a deviation between this low temperature and this high temperature. So that's what climate is, and it talks about precipitation and temperature. We'll talk about the Earth's atmosphere in this chapter, and we'll talk about ozone depletion in this chapter. So the troposphere is where all of the weather happens, all of the air circulation is happening, a lot of weather's happening here, and you have clouds and precipitation, and anyway, the troposphere is what we really care about the most in this class, but the stratosphere is also important because it contains the ozone layer. We'll talk about ozone depletion in class together, but the ozone is to define it, is 3 oxygen atoms bonded together, and it forms a pale blue color, and it's located in the stratosphere. Troposphere is where we live, and then the stratosphere is on top of that. So ozone is 3 oxygens hooked together, and it's very important for us because it protects us from ultraviolet B rays and ultraviolet C rays, and these 2 rays can really mess up your DNA and cause cancer as well. So if we don't have that nice ozone layer in the stratosphere layer, we're going to be in trouble. Unfortunately, we've decided to reduce the amount of chemicals that are going to mess up the ozone, the CFCs, chlorofluorohydrocarbons, chlorinated hydrocarbons that go up into the atmosphere. I'll talk about the chemistry, how it works in class. But in general, those CFCs that are found in refrigerants and propellants for hairspray in the 80s and the 70s, when people like to have big hair, there was a lot of people using propellants that were bad for the stratosphere. We figured that out, and we've stopped using them in general, except for maybe countries where they decided to keep using them, and for people illegally doing those things. So we've stopped using those in general, and we're seeing that the ozone is getting better, but unfortunately it takes a long time for those propellants to go from the surface of the Earth all the way out into the stratosphere. It can take up to, they decided, about 300 years. So it's going to be a while before we can figure out if we, how much we've messed up the stratosphere. So it's a really nice AP question to ask about CFCs, ozone, and the depletion of the ozone layer. So we need to talk about that in class, and I need you guys to remember that for the AP test. Weather and circulation patterns of air depend on the unequal heating of the Earth. For example, if the Earth, if the sun's shining on a beautiful normal area like Liberty High School campus, and we compare that to the sun shining on the Antarctic total snow area, it's going to be totally different how much heat goes into the surface and how much heat is reflected off the surface. beautiful white snow surface has a high albedo, and a lot of the sunlight is reflected off of it. So these unequal heating areas makes our weather pattern, makes our air circulation patterns, which affects our weather. So it's due to several things. Where the sunlight is hitting, how the sunlight is hitting. Is it hitting at a straight angle, a 90-degree angle, or is it hitting at an oblique angle? And how much surface area the sun's rays are hitting. Okay, so we'll do demonstrations like that in class so you see what I'm talking about. Air has 4 properties that affect the air circulation on the Earth, and so we need to talk and be really conversant with these 4 facts. For example, the density of the air, how much actual air particles are in a particular size, volume, is called its density. And less dense air is going to rise, and denser air is going to sink. The water vapor that the air holds is very important. So warm air is able to hold onto water vapor, which is steam, water that's in the gas phase. It's able to hold a lot more than cold air. So remember that. When air rises, the pressure decreases because of the overlaying layers that are on top of it. And so as air rises, the pressure decreases and the air expands. And the opposite happens when air goes lower. The pressure on it increases from the atmosphere above it, and the air size, it decreases in volume. So the density is going to get messed with if it's rising or it's falling. When water vapor in the atmosphere condenses into liquid water, so when you have a cloud and it changes from a cloud into precipitation, you have energy released. So I don't know if you've ever noticed this, but when you go outside and it's raining, say in the morning you go to school and it's super cold, then it decides to rain, and when it rains, actually it feels warmer. So when you have rain, you're releasing energy, because it's the opposite of when you're changing liquid water into steam. That takes energy to make that happen. So when you have the reverse, when you have gas turning into liquid, you're going to release heat. So that's called the latent heat release effect. So what happens is, on the surface of the Earth, you have the sun beating down on the tropics. And let me get to that page so I can see it myself. So, for example, we have the sun beating down on the tropics in the equator, and that's where the sun is beating down at 90 degrees. So there's tons of energy hitting this water. There's tons of ocean right there at the equator. And all of that beautiful heat energy changes the liquid water into gas, and then it starts rising. So we got this right here. So we got air that's full of water, and it's getting heated, so it's going to rise. Okay. So remember, as it rises, it's going to have adiabatic cooling, and then the water is going to condense into rain, and all that rain is going to fall onto the earth right there. So you know the tropics. If you've ever gone to Mexico, Central America, the tropic area, or you've ever been in the tropical area, it's really hot and humid and it's rainy. Usually it rains every day in the afternoon. So that's number 2. Number 3, the condensation of water vapor produces latent heat release, like I talked about just now. And this causes the air to expand and rise farther up in the atmosphere. So we're up here now. And at number 4, the warm air has to go somewhere. So it's going to start going to the left or to the right, to the north or to the south. And it's going to displace the cool air that was normally here. that cool, dry air that we just displaced is going to start sinking down, and it's going to experience adiabatic heating, and it's going to decide to flow back to the equator. So we have beautiful, nice Hadley cells, they're called, from all this work that's going on from started with the sun. So sun is the one inputting all the energy to make all that work. And in the center we have the intertropical convergence zone. So the location of this depends on where the sun is at. So it can go up or down a little bit depending on the angle where the sun is in its orbit. The Earth's orbit around it. So this is called the intertropical convergence zone, and in your book they abbreviate ITZCZ. Okay, so we got these beautiful cells right at the equator. This we also have cells that are at the north and south poles, and in between that is where we live, and those we have circulation as well in those in the zone that we live in. So we'll talk about that. So we have all these different convection currents that are going on. We talked about the intertropical convergence, and this is where the Earth feels the most intense sunlight because the sun is 90 degrees to the Earth, so there's lots of energy pushing down, going into the equator zone. We have atmospheric convection currents are global patterns of air movement that are initiated by the unequal heating of Earth. So we had the stuff going on because the sun's at the equator. We also have currents because the Earth isn't heated equally because of the surface of the Earth, and we talked about that with the north and south poles, where you have the snow and the ice, and that's the albedo effect. And then you have areas of the Earth like the ocean and compared to land surfaces. So that's what's going on here. We have the Hadley cells, which we just talked about. So they're coming up from the equator and going out to plus or minus 30 degrees, north 30 degrees and south 30 degrees. That's where that is happening. And then we also have cells, convection cells, that are happening at the north and south poles. Okay, so those are big, giant convection currents that we have on Earth. Because the Earth is always rotating, we also have currents that are formed because of this movement, and so this is called the Coriolis effect. So if you were standing here at the North Pole and decided to throw a baseball to the equator, when you threw it, it would be, if you decided to throw it straight, it would go straight. But the people who are standing on the Earth would look at it and it would look like it was curving. Okay, so that's what the Coriolis effect is. Your throw was straight, but because the people on the Earth were looking up at the ball, it looks like it's curving to them. Okay, so it depends on your orientation. But this rotation of the Earth causes winds to be curved. Okay. So the Coriolis effect, we have the Hadley cells we were talking about here, and if you're on the Earth, it's going to look like they're curved, those Hadley cells at the equator. So we have, because of the Hadley cells, we have northeast trade winds here, southeast trade winds here, and then where we live, we have westerlies. So you know that if you look at the weather, they show those circular weather patterns, and they always go from California towards the Midwest. If you watch the weather, you'll see that we always have a front coming in, or a high pressure cell or something like that, and it spins and it goes from California towards back east. So weather always on our continent always goes from California to the east coast. So from west coast to east coast, and those are called the westerlies. So important to memorize that the Earth's axis of rotation is 23.5, and be able to understand how the sun's rays are affected by that. Where you're going to have a lot of sun's power and where you're going to have less because of the location on the Earth. So we'll talk about that in class. And remember, the seasons are caused by that tilt. So this slide is going to talk about why we have the seasons, and we'll try to do a little demo of that in class so you can see that. Ocean also has currents in it because of heating as well as the salt content in the ocean and density differences. So we have ocean currents due to temperature, gravity, prevailing winds, and the Coriolis effect. And the continents get in the way. So we have all these things that are messing with the ocean currents and making them turn into big circular patterns. And in the ocean, just like in the air, when you have warm water, it expands. So when the sun's heating up the ocean water, it's going to cause these ocean currents. Gyres are the large-scale patterns of water circulation, and we have quite a few of them. We'll have to look at those and figure out where they are. And because of Coriolis, they go one way in the northern hemisphere and one way in the southern hemisphere. And so we'll talk about all these different circulation patterns, but notice that the really important thing about these patterns is where you have the upwelling. Upwelling is where cold ocean water from the deep part of the ocean is coming up to the surface, and because these currents are hitting into the continent, it's making cold water rise up and come up to the surface. And when they do, it's very, very important for fisheries and all the things that like to live on the ocean. All that upwelling brings lots of nutrients, chemicals that plants and animals really need. So upwelling is important, and it has huge effects on the productivity of these areas. So you're going to have tons of fish and animals and plants loving to live in these areas because of all those nice nutrients that they're trying to get. So upwelling is when deep waters rise up and brings tons of nutrients to the producers who support all the all the animals that live off the producers. So that's why you're going to have really good fishing along those areas. You're going to have big fisheries, commercial fisheries along those areas. We also have differences in the concentration of salt in the water, and that drives circulation. We think it's very, very important. It's very slow, but it's super important. It happens when surface waters have a lot of salt because the water's been evaporated by the sun, and those surface waters have a huge concentration of salt compared to other areas, so that makes water circulate. So the reason it happens is water in these areas freeze or evaporate, and the salt is left behind, and that gives you a higher concentration of salt in the water. This cold, salty water is dense, so it wants to sink, and then it replaces, and then the other water is replaced by that, so that causes a current. So there's big, giant currents in the ocean. They take a long time to go through this whole process, and it takes hundreds of years to happen. So if we start on number 1 here, we're going to have warm water flowing from the Gulf of Mexico to the North Atlantic, and when it does that, it's going to freeze or evaporate, and that's going to make the water saltier. So the water is saltier at step 2, and it's dense because it has more salt in it, so it drops to the bottom of the ocean, and then it comes around here, and we go to this deep cold current, that's 3, It travels along the ocean floor and connects all the oceans together. And then when we get to 4, the cold water eventually rises to the surface and circulates back to the North Atlantic. So this is due to the density differences caused by the cold and the salt content of the water. This transportation of the water, this convection of the water that's circulating through the ocean, really affects nearby land masses. For example, England and Newfoundland, Canada are exactly the same place, same latitude, but they have totally different temperature because of what the ocean's doing around them. So you might have a question about El Nino or La Nina in the AP test, so we need to talk about that. What happens every once in a while, the currents change. So for most years, let's talk about what normally happens. It's at the top there. During most years, trade winds push surface water from east to west. Okay, so it goes that direction. And right now, that's happening. When that happens, then the surface water is moving, so we have to have water to replace that. So it comes up here like this, and then you have a big, nice upwelling of all that cool, cold water. Okay, that's a normal year. When we have an El Nino year, the trade winds are the opposite direction, and it forces the hot water to go here and go the other direction. And so it affects the fisheries in that area, especially in down in Peru and South America. It really affects fishing, and it affects the weather in that area. They call it El Nino because it happens around Christmas time, which and El Nino means the baby boy, so for Christ coming that day. So that's why they call it El Nino. So that's just the reason they call it that. And the scientific thing they call it is El Nino Southern Oscillation, or ENSO. So you might see ENSO on the AP test. So remember El Nino Southern Oscillation, or ENSO. So like we said, the trade winds weaken. This weakening allows the equatorial water to move eastward toward the west coast of South America. This suppresses the upwelling that they normally have in Peru and decreases the productivity there. And this happens every 3 to 7 years. And we have El Nino, and then the opposite is La Nina. So one more thing we need to talk about is rain shadows. So rain shadows are, and you've noticed this probably when you went to Tahoe or you went to the Sierras, when the water from the ocean picks up all this moisture and it rises up onto mountains, hills or mountains. As it does that, it drops all of its rain right here. Okay, and then it goes over here, and it's dropped all of its rain, so there's no rain over here, and this is called the rain shadow. And so this is called the windward side, and this is called the leeward side. And a rain shadow means that you have no rain here, and there's lots of there's not very much precipitation. So if you go to the Sierras, you can see on this side, when you get to Tahoe, it looks really beautiful and lush. And then when you go over the top of the mountains and you get to Reno and all that stuff on that side, it's totally barren and desert-like. So that's a rain shadow. So when air moves inland from the ocean, it has a lot of water in it, and a lot of vapor in it. and it rises and it begins adiabatic cooling. When it does that, it can't hold as much liquid in the air, so it condenses into clouds, and it loses the snow or the rain. And all that precipitation is going to be on the windward side, which is on the first side, and then that cold air is going to travel to the other side, the leeward side, and it's going to descend and have higher pressures, and it's going to have and that's going to cause adiabatic heating. And the air is warm and dry, so this leeward side forms a rain shadow. There's nothing there because there's no precipitation. That's the end of this section, so stop. That's the end of this section, so I stopped on page 98, and we'll continue up 99 on the next section. Alright, I'll talk to you guys soon. Bye-bye.